Last time yesterday we were looking at logistic regression, and logistic regression is a classification algorithm, and so what we did last time was we looked at the hypothesis function for logistic regression, and just to revise, we will use uh, the function or the hypothesis that we had for linear regression, which is this one here. But what we will do is to wrap this up in another function, the sigma, or we are calling it a g function, which is going to output values between 0 and 1. So, for example, if this is the input to the function that we have, it's the function g, then this function g is going to output values like this. So, if theta transpose x is less than -4, the output would be approximately 0. Similarly, if theta transpose x is greater than 4, the output would be approximately 1. Between -4 and 4, the value of the output, the value of this function g is going to slowly rise from 0, is going to be 0.5 exactly at theta transpose x is equal to 0, and then it is going to increase and converge to 1. So that is what this function g is going to do, and it is going to uh, output values between 0 and 1. And the reason we did was because in binary classification, our y belongs to either 0 or 1. And if we do not use this function g, then what was happening was that this can be less than 0, greater than 1, or any value. There is no restriction of that. But we want this restriction because we know that our true value is either 0 or 1. Next, we looked at the interpretation that we are going to say that the output of the logistic regression is the probability estimate that the input x belongs to the class y is 1. For example, if this is my input and my logistic regression output is 0.7, then I'm going to say there is a 70% chance that the input of this size, it is this tumor of this size is malignant, and similarly 30% chance that it is benign. We also looked at the geometric interpretation of logistic regression, and basically what we saw was that the logistic regression hypothesis function, it creates a decision boundary in the input space, and on one side of that decision boundary, which is a planar decision boundary, we have one class, and on the other side we have the other class. Today we are going to look at the cost function. Okay, in case of linear regression, the cost function was this was the cost function in case of linear regression. So J was this squared loss function. But now we need to modify that as well. So we change the hypothesis function. Now we need to change the cost function and or see how the cost function should be. Okay. Okay, so this is again, just to go through the whole setup again. These are my examples, training data. So I have m examples. I can represent them as a vector. So the subscript basically means that I have n features. So x0 is always 1. We talked about that before also. And this is the hypothesis function. Okay, this is simply, you can either say something like that also. For the sigmoid function, this is the equation for how to compute the sigmoid function. The objective is to now find the parameters theta. Remember, by choosing the optimal parameter theta, we are going to basically change the decision boundary. So we want to find such a theta which is going to separate my training set according to the y that I have. But before doing that, we need to find the cost function, or we need to know the cost function, because we have to optimize or we have to compute the error based on that cost function. In case of linear regression, as I mentioned before, this is the cost function, which is a squared loss function, and it is convex. We know that, right? And convex means that you will have one minimum and not multiple, like this function here. So we have a convex function in the case of linear regression. Now what we want is a cost function uh, for the logistic regression. So usually we write it like this, that what is the cost of this prediction. So this is my prediction on the input or the training example xi, and this is the true value yi. So the cost will depend on both of these. So in case of linear regression, the cost is simply, we take this difference and compute the square. This is going to give me the cost of, on that, or the error on this training example that I'm considering. Now, in case of logistic function, this is the cost function. Okay, I'll give you a minute to actually digest that. So this is my cost function, that if y is 1, this is the cost, and if y is 0, this is the cost. So it may look complicated, but we will look at each part of it and try to see that why are we using this cost function. So first look at the case when we know that y is 1, and let's plot this part. So this is for the case when y is 1. So when y is 1, and this is my prediction, and this is the cost, or you can say j, or the cost c. So what should be the cost, higher or lower, when my prediction is 0? If I know that the ground truth is 1, if the class of the y of that x is 1, but my prediction is 0, then the cost should be
Hi.
it should be higher, right? So I expect to have something like this. This is what I want. Okay, यहाँ से I should start from here, and when my prediction is also 1, then I should get a 0 cost. So I should get something like this, and in between, I should have a curve, or maybe curve like that. Both are equivalent, or not equivalent, but both are right ways to formulate. But let's see that what does this equation, if I plot that, what will it give me? So if I plot, so minus log of 0, what is this? Because if my prediction is 0, then at this point, where should I plot it? Can anyone tell me? Compute the log of 0. What is that?
Infinity.
Okay, so minus, so it will give me infinity. Okay, so basically it is going to give me negative infinity, but since I have the minus already, so I'm going to get positive infinity. So somewhere here. Let's say I get 0.5. Then what is my error, or what is the cost? Can someone please compute it on the calculator and let me know?
So ये log base 10 है?
Log, natural log ले लें आप बेशक. Yes, please. अगर natural log है तब क्या होगा?
0.69.
ठीक है, 0.65 maybe somewhere here, and at 1 it is exactly 0. So if I have 1, you compute natural log, it is 0. So this is the shape I get, and which is what we want. के अगर आप y is 1 and you are predicting 0, then it should be the maximum error that you can have. And as you increase the probability or the prediction from 0 towards 1, it should decrease, and eventually at 1 it should be exactly 0. So this is the plot of the first part. Okay, and this is what we want also. So this is the shape for the case. Now let's look at the the second, the second part of the equation, which says that if y is 0, we want a behavior like this. Okay, when y is 0, then your prediction should also be 0. And if you get 0, then the error is okay. But if you are getting 1, then the error should be infinity or maximum. And so if you plot this, just like we did here, you are going to get a graph like that, which is shown here. So this is also what we want. So this is the cost function we are going to use. Now the only thing is that this cost function, we have written in two parts. If y is 1 and y is 0, how can we write it into single statement and single equation? We can do that by doing something like this. That look, if we multiply, if we add both of these, let's just first add them. Okay, and then I'm just writing the next part here. So what should I multiply these two parts with? That for y is, if I'm talking about y is 1, then this part should go away. If I'm talking about y is 0, then this part should go away. So what should I multiply this equation with? This equation, or different parts of this equation, what should I multiply it with? If I multiply this part with y, for example, then what will happen? If y is 1, then this is okay, that I want to use that. So y1, this is right. But if I also multiply this by y, or what should I multiply the second part with? And if I want to make it go away at y is 1.
1 minus y.
Yep, 1 minus 1. So if y is 1, then this will remain, and this is going to go away. And what will happen at y is equal to 0? Then this is going to go away, and here this is going to remain, right? So this is just a way to write it into a single way. Okay, just give me a minute. Okay. So any question about the cost function? So this is my cost function that this is the cost function. Okay. So I have now written it in one line. So any question about the cost function for logistic regression? Okay, so let's move forward. So this is the cost function for the logistic regression. The total loss function, because this part here is just for one example. But if I want to compute it for the complete data set, then I have to take the sum over all training examples. Now the only objective that remains is to minimize this cost function subject to theta. And again, the process of gradient descent will remain same. I have to repeat this, and the only difference is that the derivative is now with respect to a different cost function. But I mean, the equation will change, but the whole process is going to remain the same. And we will not be actually computing the derivative of this equation, which we will do later on, but not today. The important thing to note is that ultimately once you compute the derivative gradient of this equation with respect to the theta parameters, the equation is exactly similar to the linear regression case. Over there also, this is what we got, if you remember. So here also we have the exactly same equation. The only difference now is that this is hypothesis is now, is sigmoid theta transpose x. But other than that, the equation, it remains same. And the algorithm looks identical to linear regression. Okay, so multi-class classification. So before going over to the multi-class classification, let's have a small quiz. Please take out your paper, and we're going to do a small question. And please take out a paper, write your names, and do it with your own hand. I mean, you should not type it, but use your pen. And I will upload a link on LMS, and you have to submit the solution there in the next 10 minutes. So please get ready, take out a pen and a paper. So I am interested in the working, not only on the solution. So you have to show me the complete working of this question, not just the solution, because the solution is there. Okay, so this is the question. Use stochastic gradient descent to find the optimal theta that linearly classifies the training set. This is your training set. There are two classes, 1 and 0, and the hypothesis function is this. Again, you assume zero bias, where G is the sigmoid logistic function. Use the table below to approximate the values of sigmoid function. So this is the table to show the approximate values of the sigmoid function. For example, if the value of theta transpose x is less than -4, you say it is 0. If it is greater than 4, you assume it is 1. In between, between values -4 and 4, these are the values that you can use. Just try, approximate. For example, if you get minus 0.25, then just approximate, take one of these values. I'm just interested in the working. How do you approach this problem? How do you carry on different steps? The algorithm is like this. You have to update the theta, old value of theta, the learning rate, and the derivative, which is exactly same as in case of linear regression. So the equation is written here. Nothing is that is change. This is your alpha that you have to use. Usually alpha is, well, alpha is it should be 0.2 or it is 2. Anyway, assume alpha is 0.2. So please do that for only the first two training examples. Basically, just I want to have an output like this, just for the first two training examples in the first iteration. You have 10 minutes to complete this. So when the time, please upload it on LMS. Take the picture of the whatever you have written and upload the picture on LMS. I'm just uploading the, I'm creating a link on LMS.
एक्सक्यूज मी सर, सर अल्फा 0.2 है या 2 है?
अल्फा 0.2 है।
सर आइट्रेशंस कितनी करनी है?
आपने सिर्फ एक करनी है, लेकिन उसमें भी सारे ट्रेनिंग डाटा पे आपने अप्लाई नहीं करना, सिर्फ पहले दो जो ट्रेनिंग डाटा है उसके ऊपर आपने कंप्यूट करना है। ठीक है, बेसिकली ये जो लास्ट ये जो मैंने लिखे हैं ना, ये दो पहले दो जो स्टेटमेंट है, इन ये वैल्यू आपने कंप्यूट करनी है, इसकी आपने वर्किंग शो करनी है। और आंसर क्या पता ये ना हो, क्योंकि आई डोंट नो ये अल्फा इसमें क्या था, यू हैव टू यूज अल्फा 0.2।
और सर ये इसके अंदर लॉस फंक्शन और ग्रेडियंट वगैरह भी निकालने हैं?
I just need to find the updated value for theta, and for that theta whatever working needs to be done वो आपने करनी है. अगर उसमें लॉस भी आपको निकालना है तो वो भी निकालें, ग्रेडियंट भी निकालना है वो भी निकालें. Okay, you have this is last minute, and then please upload on CMS. और जितना आप लेट करेंगे अपलोड करना उतना ही आप पे जो है वो आपने कर्व देखा था ना इस लॉस फंक्शन का, तो उसी लिहाज से आपकी ग्रेडिंग होगी इस तरीके से. जितना आप लेट करेंगे उतना ही आपके मार्क्स कम होंगे. Okay, so please upload on CMS, on LMS. Okay, so let's continue that what if we have, instead of binary classification, we want to do multi-class classification, which means that y can be, maybe it will still be discrete, but it maybe let's talk about 3 classes. So it may be 1, 2, 3, or more than 3 classes. So how can we modify or update the logistic regression for the multi-class classification? And the algorithm is called Softmax regression. It is the generalization of logistic regression, and we can call it Softmax regression. The example of multi-class classification is that if we want to tag emails, for example, if we want to tag it, okay, whether the email belongs to work category, friends category, family category, hobby category. So there are 4 categories, 4 discrete labels. This is a multi-class classification problem. Medical diagnosis, you have maybe 3 classes: not ill, cold, flu, etc. So you have again multi-class classification problem. Whether it is sunny, cloudy, rainy, snow. So this is again a multi-class classification problem. So how do we approach the multi-class classification? Softmax classification is the generalization of logistic regression to the case where we want to handle multiple classes. That is why now will be from 1 to k, where k is the number of classes that you have. Hypothesis function is, we want the hypothesis function to estimate the probability, this probability for each value of k is divided to 1 to k. What this says is that now before we had just one output. Okay, in case of logistic regression, where there were only 2 classes, we had only 2 outputs. So it was enough to predict one probability. So it was enough to predict this probability, because the probability that it belongs to the other class we can easily compute using 1 minus this probability. But now, since we have multiple classes, we want a probability estimate for each of those classes. So we want that our classifier should predict this probability, as well as it should predict y is 2 given this, as well as y is equal to k, where k is total number of classes. So we want to have k predictions, 1 for each class. Okay, so this is how we are going to depict now. We want a vector. So the hypothesis output is a vector. Each element of that vector is the probability that the input x belongs to that particular class. Okay. So this is basically softmax regression. Let's see how can we now obtain this probability. What we are going to do is that before, so this was before, this is what we want now. This is the prediction before. What we are going to do now is to compute this value for each class. So let's look at this one here. So this is, this is my prediction now for the first class. Similarly, the second class and the kth class. So what this tells me is that I have these theta parameters for each class. So I will have, theta 1 is depicting that this is the theta parameter. It is again a bunch of vectors. Similarly, theta 2 is the parameter for the second class, and so on. So using each of those parameters, I'm going to compute this value, exponent theta transpose x. And I will divide this vector by c. And what is c? C is a normalization constant, which is going to normalize all these values so that the sum of all these values is 1. And how can we do that? We can do that by taking the sum of all these values, of this vector here. This is the sum of the vector, and dividing each element by this c. What this is going to do is to make sure that if I take the sum of all these probabilities, then I get 1. And this is what I want, because if I have 4 classes, for example, then I want that the, or let's say if I have 3 classes, then this is what I want. The probability that the input x belongs to class 1 plus the probability that it belongs to class 2 plus the probability it belongs to class 3, they should sum up to 1, or otherwise it's not a probability distribution, right? So this is what we want here, and this is how we achieve that. First, we use the different theta parameters for each class and use that to compute this value. And finally, we are going to divide by the sum of all these values to get the probability for each class. So this is the cost function now. In the previous slide, I wrote it in the using vectors, but if you want to write it, this is my cost function. So let's look at it in detail. If you change k from if you let k is equal to 2, then you will see that this basically reduces to the logistic regression loss function that we have already discussed. So this is just the generalization that if it is greater than 2, then this is what you have. But if you change it to 2, then basically you get the loss function for logistic regression. And for greater than 2, you can see it like this, that this summation is for each class, and then you have the probability of belonging to that class here, and then you do that for all the training examples. Okay. So for example, how can we see that it is doing the right job? For example, we know that, let's forget about this for the moment. Let's forget that this is there, and we are computing the error just for one example, for one training example, and that training example is xi. Its ground truth label is yi. So let's look at this. So we know that this part here is the probability that it belongs to a particular class. And if, let's say, we know that the ground truth label is 2, for example, then this portion of the equation, it will be 1 only when k is 2, right? And so this equation, what it is doing, it is telling you that the loss function would be minimum when you are predicting right, when you have a correct prediction. Otherwise, the loss function will have a bigger value. right? Can you see that? Because you know I also have this negative also here. And this is the case when we set k is equal to 2, then this loss function generalizes to reduces to the logistic regression loss function that we have already looked at. Okay, so this is exactly the same. And now we have to compute the gradient descent with respect to this new loss function. And you know, ultimately things become very easy that you know what you're doing exactly is not different from what we have been doing for logistic regression or logistic regression loss function. So I know that I have gone through this in very quickly, and the idea is that once you know the logistic regression loss function, then softmax or multi-class regression is very similar to that. And we have gone through the equation and then discussed that the loss function that it reduces to logistic regression loss function if you make the number of classes equals to 2. Okay, so any question? Any question? If there are no questions, then we can sign off and meet next week. Or, I mean, on Friday you have the lab also. Look, I think